I wish all of the success, and I instruct you to start the differential. Thank you.
Thank you, sir. Respected professors, respected external Dr. Paresh Kumar Nayak, sir, respected Dean Academics, respected Dean Strict, and my DS members, respected Madhav Chandra Tripathi, sir, respected Srivastava Behra, sir, my supervisor and my co-supervisor, and all the faculty members, my juniors, my batchmates, and my students. My name is Swain, bearing registration number 202210703, Ph.D. research scholar. I was enrolled in 2021, registered in 2022, and defending my thesis in 2025. My thesis title is Performance Improvement of Circuits and Systems to Design and Analysis of Fractional-order Elements in School of Electronic Science, OUTR, Bhubaneswar. This is the outline of my entire work. First comes the introduction part, then motivation and objective, then research works and results, conclusion and future scope, and finally the references. Now, coming on to the introduction to fractional order elements. Generally, it can be seen that fractional order circuits are defined by fractional order differential equations. Fractional order differential equation is used to generalize fractional capacitor and fractional inductor. Generally, there are three circuit elements: resistor, capacitor, and inductor. Resistor has a phase shift of 0. The capacitor has a phase shift of -90, whereas inductor has a phase shift of +90. But if we are talking about a fractional capacitor, its phase lies somewhere between 0 to -90, and a fractional inductor, its phase lies between 0 to +90. But it has to be a constant phase behavior. And if we are talking about the transfer function of fractional capacitor, it's 1 by Cs to the power alpha, and of a fractional inductor is Ls to the power beta, where alpha and beta are fractional values or values from 0 to 1. Now coming on to my research gap. The concept of fractional order came into existence in 1960s, whereas the experimental realization was first carried out in 2006. However, the design, realization of fractional order circuits using fractional capacitors are still lagging in literature. Also, the hardware realization of fractional inductor till date has not been achieved. Besides, most of the fractional order filter using fractional inductors and capacitors are simulation or emulator based, and application of two-terminal fractional order elements in different analog circuits are yet to be experimentally validated. Now coming on to my motivation. Incorporation of fractional order elements enhances the performance of circuits and systems. Hardware realization of two-terminal fractional inductor order less than 0.5 are yet to be developed. Frequency range of analog circuits can be changed without changing the circuit coefficients or the RC time constants. Application of two-terminal fractional inductors in different analog circuits are yet to be validated. Hence, it is of great interest to design, realize, and study the performance of fractional order circuits with two-terminal FC and FI, that is fractional capacitor and fractional inductor, and experimentally compare their performance with its integer order function. Now, coming to my objective. These objectives reflect each and every chapter of my thesis. First one is to investigate the characteristics of fractional order symmetric slope bandpass filter using switched capacitor, to present the hardware realization of switched fractional capacitor, then a fractional order bandpass filter using switched fractional capacitor, to first time implement a two-terminal fractional inductor of order less than 0.5 and study its performance, to realize a wideband fractional order bandpass filter using two realized fractional capacitor and these fractional inductor. Again, to use these fractional inductors to realize a wireless power transfer system. And now we will be coming to our methodology. Here, the fractional capacitor and fractional inductors, they follow these transfer functions where alpha and beta are the coefficients which are in between 0 to 1, and in simulation studies the approximation methods have been used in MATLAB as well as in LabVIEW using the FormCom toolbox to design these fractional capacitors and fractional inductors, and in experimental, we have used RC ladder network and zirconium-based fractional inductors for experimental hardware realization. Now coming to our chapter 2. Realization of optimized fractional-order symmetric slope bandpass filter using switched capacitor. Coming on to the outline, the design and modeling of fractional-order bandpass filter with fractional capacitor have been realized addressing frequency and time domain series. The exponents of fractional capacitor has been optimized using genetic algorithm, where it improves the quality factor from 0.44 to 11.45 without changing the time constant of the circuit. The performance parameters of the proposed circuit evaluated and validated experimentally, then observe the settling time and the response speed improves. Now, this is the two-stage fractional order bandpass filter using 4 fractional capacitors. These are the transfer function of the stage 1 and stage 2, and considering both stage 1 and stage 2, the simulation studies have first been carried out. First, considering stage 1, these are the frequency domain analysis varying the order alpha, that is the order of the first capacitor, and varying the order beta, that is the order of the second capacitor, one at a time. And these transfer function has been optimized using genetic algorithm to find out at which orders the filter will give us the highest quality factor. And it has been found out that at order 0.3 and 0.7, the maximum quality factor has been encountered, and this is the magnitude response of the fractional order bandpass filter incorporating orders of the fractional capacitors 0.3 and 0.7. Now coming to stage 2. In stage 2, using those orders in the first case, the stage 2, considering stage 1 and stage 2, we are varying order alpha 1 and beta 1. Those are the orders of the third and the fourth fractional capacitors used in the circuit. Then, after obtaining all the possible responses, we have seen that at order alpha 1 equals to 0.7 and beta 1 equals to 1.9, it gives us a nearly symmetric slope bandpass filter with very high quality factor. Now, obtaining the stability analysis of the fractional order bandpass filter. Here, this is the criterion for stability in case of a fractional order system. In case of a general system or a classical integer order system, the poles, if they lie on the imaginary axis, then it is marginally stable. In the left hand side it's stable, in the right hand side it's unstable. But in this case, there is something different. Respected Honorable Vice Chancellor Sir, I would like to present my research and defense today, and we are currently under chapter 2. Here, if you are talking about the fractional order system, the stability goes in this way that this angle is no more 90 degrees. This is alpha pi by 2. If the order of the fractional capacitor decides its stability boundary, and here it has been seen that this is the stable range and this is the unstable range for the system, and obtaining the pole locations in simulation level, it has been seen that the two poles are close to the stability boundary, and as reported by Professor L. Wakil in 2012, that if at least one pair of poles are close to the stability boundary, then the quality factor of the system is extremely high, which is also proved in this simulation study. Now, the 4 resistors in this filter have been replaced with 4 switch capacitors, and here the time domain analysis has been obtained using the where the equivalent resistance and the switching frequency are shown both at the same time, and the switch capacitor-based fractional-order filter has been carried out in simulation level both in MATLAB as well as in LabVIEW with a very negligible error, because these two softwares use two different kinds of methodology. In case of LabVIEW, we are using the power of the transfer function, but in case of MATLAB, we are using approximated fractional capacitor in ladder network. Now coming to the experimental results, Here we are using RC symmetric poster one representation of the fractional capacitor in GIC network for obtaining an order of greater than 1, and this is the experimental setup. The simulation result is the red one and the black one is the experimental, and the values are given in this table, and this is the time domain analysis. The red one is the simulation part and the black one is the experimental part, and these are the simulated results, experimental results, and the corresponding error percentages. Now, in this chapter, we have seen that at optimized orders 0.3, 0.7, 0.7 and 1.9, we achieved a quality factor of 11.47. The filter achieves a nearly symmetric slope response of plus 21.9 dB per decade and minus 21.3 dB per decade. And here, the quality factor, the roll-off rate, the maximum peak and the rise time all held on minimum to minimum error percentages as comparing the experimental with the simulation part. Now, though this filter ends a very low settling time, but still this settling time is very high. Therefore, we want to, in order to improve the settling time, that is decreasing the settling time, decreasing the roll-off rate, decreasing the maximum peak, we are replacing the capacitor with fractional capacitor in the switch capacitor. That is, we are using switch fractional capacitor in our upcoming chapter, that is chapter 3.
These copper vibrating hybrids, copper hybrids, does not really
Now, chapter 3, realization of switched fractional capacitor-based fractional-order bandpass filter. Here, the capacitor of the switch capacitor has been replaced with a fractional capacitor. Here, our main goal is to realization of design fractional-order bandpass filter having these three combinations: resistors and fractional capacitors, then switch capacitors and fractional capacitors, then switch fractional capacitors and fractional capacitors. This is the circuit diagram of our proposed bandpass filter. This is the transfer function of the fractional order bandpass filter, its frequency domain and its magnitude and phase are given by these equations. And the frequency domain analysis has been obtained by varying one order at a time from 0 to 1 with a step of 0.1, and the quality factor has been calculated mathematically where alpha and beta order have been represented with the quality factor in this equation. Here quality factor, then the time domain analysis has been obtained using MATLAB as well as LabVIEW, and the settling time has been seen having 124 seconds. These are the MATLAB values and these are the LabVIEW values for the time domain parameters. Now incorporating switch capacitor, these are the switching frequencies. We are varied from 50 Hz to 500 Hz. These are the corresponding switching frequency of both the switch capacitors, and this plot shows the switching frequency, how it is depending upon the settling time and the rise time of the fractional order bandpass filter. It has been seen that if the switching frequency is between 100 to 300 Hz, it gives more favorable results of low settling time, and it has been seen that the minimum settling time, that is 4.03 seconds, is achieved at a switching frequency of 100 Hz. Now incorporating switch fractional capacitor. Here, using switch fractional capacitor, the orders of the capacitor in the switch capacitor used in the bandpass filter has been varied from 0.2 to 1.0, one at a time. Both the fractional capacitors in both the switch capacitors have been varied, and these orders have been optimized using particle sum optimization algorithm, and we are observing the rise time, the peak overshoot and the settling time with respect to delta and lambda order, and the optimized order were 0.2 and 0.6, for which the minimum settling time, the minimum peak overshoot and the minimum rise time has been achieved. Now these are the experimental results, where this is the experimental frequency domain results. The blue one shows the integer order filter, the red one shows the fractional order filter, and the black one shows the experimentally designed fractional order filter. And these are the frequency domain parameters, the MATLAB simulated values, experimental results, and the corresponding error percentages. Now coming on to the time domain experimental results. Here the switching frequency are 100 Hz, 200 Hz and 300 Hz. As I said earlier in the simulation result, from 100 Hz to 300 Hz, it gives precise results or the least settling time, rise time and peak overshoot. And these are the corresponding peak overshoot, rise time, settling time in the simulation part, the experimental part and the corresponding error percentages. Now coming to the experimental validation of switched-fractional capacitor, where the switching frequency is kept at 100 Hz as found in the simulation, and the orders as optimized using particle sum optimization, that is 0.2 and 0.6. We have the experimental result and the simulation result marked as black and red. And this graph shows finally the fractional order filter at alpha equal to 0.3 and 0.7 and the two resistors. Then those resistors were replaced by switched capacitors. Then those switched capacitors were replaced by switched fractional capacitors. In this way, the performance goes on improving. That is, the settling time, the rise time, and the peak overshoot slowly decreases. Now coming on to the summary part, the orders were 0.3 and 0.7. The quality factor was 0.44, and here using switched fractional capacitors of orders 0.2 and 0.6 decreases the settling time from 19.1 second to 1.32 second, rise time from 0.54 second to 0.051 second, and peak overshoot from 0.133 to 0.019. Now, from chapter 2 and chapter 3, we have designed fractional capacitors, used that in filters, designed switched capacitors, used fractional capacitors in switched capacitors, and many more. Now, we need to explore fractional inductors, which is also an integral part of the fractional order elements. Therefore, we have proposed a fractional inductor in the next chapter. Implementation of a fractional inductor order less than 0.5 and its performance study in a high frequency integrator circuit. First time, a two-terminal fractional order inductor of order less than 0.5 has been designed and realized using zirconium quantum dots diluted in ethanol. The fabricated inductor operates between a temperature range of -10 degree to +45 degrees Celsius and has a lifespan of more than 1.5 years. This has been realized and also been used to design a integrator circuit. Now coming to a fractional inductor, it has a transfer function of Ls to the power. Here we are using transverse electromagnetic mode. In case of a transverse electromagnetic mode, if we have a conducting core of copper and it has a conducting wire in between and the space is covered with a conducting core, then the transfer function has a root over upon it, which gives an order of 0.5. Now, in order to decrease the order further from 0.5, we have used zirconium quantum dots because we needed to have a conductor which has a property of a semiconductor. Therefore, we have used zirconium, which has been synthesized in one-pot method that has a semiconducting property which can be seen from these images. It has a band gap of 5.07 electron volt, which qualifies them as a semiconductor but in quantum state. Zirconium quantum dots have been varied from 10 ppm to 100 ppm in ethanol solution, and experimentally we have performed the analysis to obtain the results of fractional inductor. Here, this is the frequency versus the alpha value of the fractional inductor for different concentrations of zirconium quantum dots used in the core. Now, obtaining the frequency domain analysis of the fractional inductor at 0.22 order that has been achieved at 100 ppm, 0.32 order achieved at 25 ppm, 0.25 order achieved at 50 ppm, and 0.38 order achieved at 10 ppm. These are the concentrations of zirconium quantum dots in ethanol, the corresponding fractional inductance, orders obtained from the magnitude plot, orders obtained from the phase plot, operating range, experimentally obtained operating range, its functional frequency range, and the corresponding error percentage. Now moving on to the experimentally obtained time domain analysis of those inductors. From the previous frequency domain analysis, we had obtained the orders and the fractional inductance values. Using those orders and fractional inductance values, we had also done the simulation part. In the simulation, these are the simulation obtained for the fractional inductors, and these are the experimental comparison with the simulation result of the fractional inductor at 4 concentrations of the zirconium. Those gives orders as 0.22, 0.32, 0.25 and 0.38. Now, in order to check the robustness of this device, we have obtained the temperature change with respect to fractional order. It has been seen that from -10 degrees Celsius in refrigeration mode to +50 degrees Celsius has achieved using a heater. These are the response of the fractional inductor. It shows at very less order, the slight deflection is shown at less than 0 degree and higher to 50 degree or higher to 45 degree. But rather than that, all the other orders remain constant with respect to temperature, and these are the plots showing its performance with respect to days. That is, it performs extremely good till 1.5 years or till 2 years. After that, shows slight fluctuations. Now moving on to the experimental analysis of the fractional inductors, parasitic, that is the parasitic analysis. Here, the resistance value and the capacitance value, the parasitic resistance and the parasitic capacitance value of the fractional inductor has been obtained. Where the resistance along with the losses are these values corresponding to the concentrations. Its corresponding capacitance value which is extremely low and can be neglected, and the inductance simulated, the inductance obtained from the LCR meter experimentally, and the corresponding error percentages. Now, design and analysis of fractional inductor integrator using fractional inductor. Now we have, in order to obtain how this fractional inductor performs, we have used a integrator circuit where we are using a fractional inductor, and these are the frequency domain analysis at different orders obtained in simulation level, then experimental comparison with the simulated result, and this table shows the simulation result, the experimental results, and their corresponding error percentages. Now coming on to the summary part. Here the novelty of the work is first time a design of fractional inductor providing an order less than 0.5. It has been observed that zirconium quantum dots have been used in different concentrations to provide different orders of the fractional inductor, and varying the concentration from 100 ppm to 10 ppm, the order increases from 0.22 to 0.38, and the inductance from 150 milliamp to 25 milliamp. And this fabricated fractional inductor works seamlessly between a temperature range of -10 degrees Celsius to +45 degrees Celsius with an aging of 1.5 years. Now, we have designed a fractional inductor. In order to check its applications and design various applications, first we have designed a wide band fractional order LC tank filter using this fractional inductor in the next step. That is realization of a fractional inductor based wide band filter using LC tank configuration. Here, the wide band fractional order bandpass filter using 2 realized fractional capacitors and 2 fractional inductors has been used. The stability analysis and the frequency response has been investigated. Seen that reducing the fractional exponents, that is alpha and delta, increases bandwidth to microwave. Now, experimental results of the time and frequency domain as the filter achieves a experimental error of 7.5% in a settling time of 83 nanoseconds. Now, these are the simulation results corresponding to the transfer function with these values, the capacitance values and the fractional inductance values, and these are the 4 simulation magnitude results of the filter. Now, the orders have been carried as follows, and these are the corresponding center frequencies, the bandwidth range, the approximated bandwidth and the corresponding quality factor. It has been seen that when the orders are reduced, the bandwidth increases. Now seeing the time domain and the stability analysis, this is the time domain analysis corresponding to these orders of alpha, delta, and these orders of beta and gamma, beta and lambda. And here we are showing the stability analysis. As I have said in chapter 2, the stability criteria has also been re-shown here, where this is the unstable range, the green one is the stable range, and the filter's characteristics have been seen to between these ranges, and this has been shown in this plot, simulation plot. These are the pole locations, the corresponding values, and the zero locations. These are the fractional order combinations and the corresponding pole locations. Now coming on to the experimental results. This is the simulated result from using beta equals to lambda equals to 0.5 with alpha and delta carried from 0.22 to 0.40, and these are the corresponding experimental result and their comparison. This shows the fractional order, corresponding simulation values, the experimental values, and their corresponding error percentages. These are the experimental results obtained from time domain analysis, the simulation values, the experimental values, and the corresponding error percentages. Now coming on to the summary part. Decreasing the fractional exponent beta and lambda from 1.0 enhances the flatness near the lower cutoff frequency. It gives us a very high bandwidth at error percent of 8.6%. Using fractional orders alpha equals to delta equals to 0.22 and alpha equals to delta equals to 0.22 and beta equals to lambda equals to 0.5. This achieves a minimum settling time of 83 nanoseconds at the error percent of 2.7%. And in this chapter, we are examining the filter characteristics using fractional inductor. Now we are using the fractional inductor not only in signal processing but also in power electronics, where we can see its behavior in mutual inductance as well as in wireless power transmission system in the next chapter. That is design analysis of wireless power transfer systems using fractional inductors. Here the same proposed coaxial based fractional inductor with zirconium quantum dots has been used. The fractional order mutual inductors have been evaluated experimentally through comprehensive frequency and time domain analysis, and it has been seen that the wireless power transfer system utilizes fractional inductors for both transmission part and the receiving part and achieves a maximum efficiency of 85.2% while transmission of energy at a range of 100 to 120 cm, charging a 1.2 volt battery in just 360 seconds. Now moving on to the mathematical part of it. This is the equivalent circuit of a fractional inductor based mutual inductance, and this is its transfer function, the frequency domain, and here mathematically the mutual inductance, the fractional order mutual inductance has been evaluated, and these equations have been used to plot these two 3D plots showing the impedance with respect to alpha, beta and the gamma, where alpha and beta are the orders of the transmitter and the receiver, and gamma is the order of the mutual inductance. And here, this is the mutually coupled fractional inductor. They are using two fractional inductors in zirconium quantum dot 4 ethanol solution, and this is the experimental plots where we are using and we have obtained the primary and the secondary coil transfer functions, and we have experimentally we have obtained the frequency domain analysis of the primary part and the secondary part from the oscilloscope. Then fractional order inducting coil power transfer circuit, where we are using a common core solution as well as with the transmitter circuit and the receiver circuit, and these are the experimental setup and these are the experimental results showing the magnitude part and the phase part with respect to different corresponding orders of the fractional inductor. And here the output power equation has been derived mathematically, and the center frequency at which the power is maximum has also been derived mathematically. Now coming on to fractional order inductive coil power transfer system, where output power and the power efficiency has been shown in these two plots. Here we have a common code solution. In that common code solution, we are seeing the input power and the output power, input voltage and the output voltage. These are the concentration of the Zirconium quantum dots, the numerical simulated maximum power, experimental maximum power, the numerical simulation percentages, efficiency percentages, and the experimentally found efficiency percentages. Now we are going to the mathematical representation of fractional inductor-based power transfer system, where we are having a distance between the inductive transmission coil and the inductive receiver coil. This has been obtained mathematically. The equation showing the mutual inductance of the transmitter and the receiver part, and this equation shows the power for the wireless power transmission, and this shows the efficiency of the power. This circuit shows the block diagram of the entire fractional inductor based transmitter, receiver, and using these circuits for the proper examination of fractional order wireless power transmission system. Thank you. Now moving on to the experimental analysis. Here we are putting the transmitter section and the receiver section at a distance of 30 to 60 centimeter. Then we are increasing to 80 to 150 centimeter. Then 200 to 250 centimeter. These are the corresponding frequency responses with respect to the power as well as the output voltage power and the efficiency. Here it shows the distance, the output voltage, the maximum output power, and the maximum efficiency. Now here we are using a 3 centimeter fractional inductor, which has a very low inductance. Therefore, in order to increase the efficiency of the transmission from the transmitter part to the receiver part, we are increasing the size of the fractional inductor to at least 12 inches. This is the new proposed fractional inductor of 150 mm using with a width of 20 mm. And using that, first we have obtained the frequency domain analysis showing whether its performance as a fractional inductor, where it shows the alpha value and the beta value of 0.15 to 0.2, which qualifies it to be a fractional inductor first. Then we have done the experimental analysis, and these are the constant phase behavior, the roll-off rate, the operating frequency, and the fractional orders. Then we have used that in the transmitter part and the receiver part, where we are having a distance of 500 centimeter. This is the receiver section, and this is the transmitter section, and this is the receiver section. We have an output voltage. This is the graph of output voltage with respect to the distance, and this is the graph of output power with respect to distance, and this is efficiency with respect to distance. When we are increasing the distance, the power of the efficiency is decreasing. Now, this graph shows the realization of wireless power transmission system, which can be used for charging a battery. Because first we have giving different input voltages starting from 1 volt to 5 volt. We are observing the output voltages with respect to distance and the output power with respect to distance. Here, these are the fractional orders, the two fractional inductors designed, the corresponding inductance values, maximum power voltage that it can transfer, the maximum output power it can transfer, and the maximum efficiency. Where it is given that at order 0.16 and an inductor of 1.24 Henry set 1 minus alpha, it gives a maximum power of 426 milliwatt with an input power of 500 milliwatt. We have a maximum efficiency of 85.2%. So this can be used in charging a battery of 1.2 volt. And this graph shows the the charging time of the battery, the charging and discharging time of battery, and this has been repeated for 100 cycles to see its performance, and it has been shown in this log time graph. Now, in order to see its performance, we have also used different kinds of barrier in between the transmitter and the receiver part, and using conducting barrier as well as non-conducting barriers, it showed no deflection. And we have also seen different barriers like in-house barriers, suppose books, copies, human, and it shows the efficiency percentage with respect to the barrier length. It shows negligible deflection. Now coming on to the summary part, the practical reality of fractional order wireless power system is demonstrated, which in charging a battery of 1.2 volt in 360 seconds at a distance of 200 centimeter, and the research underscores the transformation of potential fractional inductors in enhancing the power transmission efficiency to 85.2%, and it can give future advancement by improving the power. Suppose we need to improve the efficiency, we need to give very high input power, which was not practically possible at that time, but currently we are developing such devices which can give an input power of nearly 20 watt, which can be used for higher applications also. Now coming on to my chapter 7, that is conclusions. The applications of fractional capacitors and in fractional filters and switched fractional capacitors has been shown here. The experimental validations of different frequency and time domain components, measures of realized fractional order circuits, implementation of a single component fractional inductor and its application in fractional order wideband filter, and experimental realization of mutual inductance and its performance study in a real-time wireless power transfer-based battery charging system. Now coming on to my future scopes, implementation of sensors. Different kinds of sensors can be used using fractional capacitor and fractional inductor, but the core part is our measurement, and tunable fractional inductor and tunable fractional capacitor can be designed in future, and modeling and optimization of complex biological growth such as cancer, dengue, this can be done using fractional order dynamics or fractional calculus. Bioimpedance analysis of fruits and vegetables can be developed using biosensors using fractional capacitors and fractional inductors also, and realization of fractional order supercapacitors for power factor correction, it can be done using fractional capacitors. Now these are the questions which have been asked esteemed external reviewer, and these are the bio questions, and sir has asked that this in section 6.5.1 and 6.5.2 the wireless power transmission system using high inductance fractional inductor is demonstrated and used for charging a battery of 1.2 volt and 0.5 volt. The scholar is required to give a practical example of the requirement for charging 1.2 volt battery. Sir, here we are planning to use this 1.2 volt battery for charging the pacemaker battery, which is the replacement and the maintenance is quite tough, and also contactless energy solution for low voltage industrial sensors. It can also be used in those situations. And the second question is the requirement of high frequency supply transformers and rectifiers. This has been given in the next part. As far as answered the complex arrangement, whether it is cost effective or not. Sir, the fractional inductor based wireless power transfer, this is the first time I am doing, and wireless transmission of power with the efficiency of 85.2% is very high, which is presently not achieved using fractional order systems. Therefore, if you are looking at the cost part, only the cost of the copper tubes and zirconium quantum dots are the major cost. And zirconium quantum dots was also synthesized in one hot method in our university only by the chemistry department.
See, you have shown one inductor.
Yes, sir.
Yes, sir. Then you are increasing to length.
You are able to transmit higher order.
So in that case, what will be size? For example, for this. inside our body, we want to charge something like battery, and just you tell me in layman, I don't know what will be your input and what additional requirement you need to transmit this power to this. Which power actually, what will be your input actually?
So input will be a high frequency voltage.
What will be your voltage?
So presently we are experimenting using 5 volt. 5 volt at a frequency of 20 megahertz.
So we will get 5 volt.
So from the frequency generator now we are giving, but we can
5 volt with AC or DC or
AC.
AC. Where we are increasing frequency.
Yes, sir, to 20 megahertz.
How do you increase frequency?
Sir, we can use currently we are giving this using frequency
5
generator.
volt AC actually will better. Will convert you to convert.
Yes, sir, we have to convert the DC part to the AC part first.
And what you have shown actually 100 meter, centimeter to 400 centimeter.
Yes, sir.
Is it for normal inductance actually? Because in air gap actually magnetic coupling is very less.
Yes, sir.
There while you are still using high frequency efficiency 85%.
So mathematically
100 centimeters.
Yes, sir.
Because for example here electric vehicle
Yes, sir.
is just
15 centimeters.
15 centimeters right there, and therefore your surface area is very large, so that magnetic coupling through air it will be there, but it will be better. So here again in between also some condensing, some surface, I don't know exactly, but somewhere I have seen in between what is transmitter and receiver, intermediate some conducting elements are also introduced to increase the coupling. But here longitudinal coupling with 400 centimeter, 400 centimeter means 30 centimeters.
2 meters around. I mean 6 feet. Around 6 feet.
Actually, 100 cm is 1 meter.
1 meter.
200
1 meter is around 3.3 feet.
And another thing to try to just explain how we are preparing that fractional order inductor principle. I don't know.
Yes, sir.
Just
here we are
experiment you conducted. So what is normal capacitor? Suppose I will purchase, for example, 5 microfarad capacitor, 10 million inductor. So like that. But use how to represent it. For example, for me, normal capacitor inductor 5 microfarad. So 5 million inductor. Similarly, what will be your fractional order capacitor and inductor, and how to get them? That's value of inductor capacitor.
So here
Experimental.
So experimentally first our key goal is to have order less than 1.
Yes.
First thing. So for that generalized core-based fractional inductor, it is till yet not possible to get that order. Therefore, we are using the TEM model, the transverse electromagnetic mode model. We have a copper tube. In between that, we have a copper wire, and there is a conducting core. The rest of the parts. In that case, it gives an order of 0.5. It was done earlier. Now we are replacing that conducting liquid with a semiconducting liquid.
Which liquid?
That zirconium quantum dot diluted in ethanol.
Inside the rod is there. Yes. And the
Outside.
surface.
The inside part is the anode part and the outside part is the cathode part. And in between,
some
solution is there.
And by doing this, we are able to.
Yes.
And how to measure accelerator?
Sir, we are obtaining the frequency domain analysis, and from frequency analysis, the phase part at 2 decades.
Okay, that phase difference will tell you the what is fractional like
Yes, sir.
the
alpha
minus 90 degree
Yes, sir.
capacitor.
Divided by 90, we will get the order.
Phase angle between what voltage?
Yes, sir.
But that distance actually coupling to transfer this much of power is very difficult. I think. Because you see the large surface with small distance, and therefore they are making so many arrangements which there is magnetic resonance. From magnetic resonance, they are transmitting power from transmitter to receiver. Means suppose AC voltage is there, they are making it DC with DC to high frequency AC. Then with resonance power transmission is expressed at high frequency. For high power applications.
Lithium ion.
That is high. But 1.5 volt battery is what is the size actually?
Small size.
That cannot be placed inside body.
No, sir. That is for the prototype model. We have not actually, but
Last time we have come from this concept of utility.
Concept.
No power transmission is down classical electricity. After this problem, so that means there are some actually commercial availability and commercial.
The low power actually for inside body actually if you want to charge some pacemaker or something that it is required. You cannot replace it. So, or then externally it will be able to charge. It will not do. So that means I did not know, but in here by just calculating the phase, then you can say that this is fractional inductor inputed and 0 to minus 90, 0 to plus 60.
but it should be constant throughout some frequency range. And these are all my publications in international journals.
Then to verify that, we have to do Gibbs analysis.
Yes, sir.
And another thing, something you have written 1.5 years,
Yes, sir.
something like it.
Actually, first when we started doing it, it gave us result and we kept that
Given
device.
time to degrade.
Yes, sir. It is degrading, but with very low degradation is taking place, which is negligible in case of our experimental analysis.
We will know that after 1 year it will not.
Yes, sir. Because, sir, when we started doing that work, took the result. Then
You
we,
see, you are having material, you
Yes, sir.
compare the material experimental inductor,
Yes, sir.
fractional-order inductor, capacitor. Then you have conducted experiments today. After 6 months,
after 3
with
months,
same material,
yes, sir.
if you conduct
Same
then
device also.
you are getting some change in the phase.
Slight change in the phase as well as in the drop in magnitude. We also get that because since it is ethanol, some part evaporate because we are making a prototype.
That's
for
why
the-
it's after this time it will
It will
release
adjust.
behavior characteristics.
And these are my international conferences which I have done.
And how that phase is related to alpha 0 to 1.
Phase divided by 90 equals to alpha. Because if the phase is 90, then alpha
Suppose
is
you
1.
get 45 degree phase.
Phase is 0, alpha is 0.5.